When we're faced with a linear first order equation and we want to find its solution, so solve for y, the technique we're going to apply that's going to work in general for first order linear differential equations is this method of an integrating factor. What we're going to do is multiply the entire equation by m, and we're going to choose m carefully using this formula here. So notice that this has to be in standard form for our next step to work correctly. What we do is grab the coefficient p of t. That's the term that's in front of the y. There's nothing in front of the y prime. It's going to have a coefficient of 1. So we grab the coefficient of the y and put it inside an integral and an exponential, and we'll see why this makes sense. And the next step is going to be multiplying the standard form of the dE by m of t, or m of x if that's your independent variable. So let's see how that plays out. We're going to literally take this m and multiply it through. So we're going to have e integral of p of t times y prime plus p of t times y. That's multiplying on the left. Then we have our equals q. And there we just have the product of q with that exponential. Now, that doesn't seem particularly helpful yet until we get to the next stage. We're going to multiply this in onto both terms. And here we get e integral p of t dt times y prime plus p of t e to the integral p of t dt times y. And the right-hand side's identical. We don't do anything there. But if we look through this lens here and look through the lens of the product rule, what we see is, let's call it g prime, and let's call this f. And if we call this g, then if we look carefully at this whole term here is f prime. Think of what we'd have to do if we differentiated f with respect to time. Well, the derivative of an exponential is the same exponential, and then we take the derivative of the exponent. Well, that brings the exponent down, and the derivative gets canceled by the integral, and so we end up back to p of t. And what this does is guarantee that what we have is the derivative of simply the exponential times y. This, it seems so simple to say this, but it catches people all the time. This left-hand side is exactly equal to the derivative of this exponential times y. If you apply the product rule, you'll expand to this. We're not integrating yet. We're simply noting that what's written here could be written this way, with the right-hand side staying exactly the same. And once we've done that, then we can do some more work. But this key observation that starting with the standard form, finding this integrating factor, and multiplying the entire equation by it, so not changing it, just multiplying everything by that integrating factor, will guarantee that the left-hand side could be rewritten as the derivative of a product when we're done. And we'll see how that helps us solve equations in the next example. We note here we have a differential equation in standard form that's required for this integrating factor to work, and the coefficient of the y is what plays the role in our integrating factor. So our integrating factor, here our function is a function of x, so our integrating factor will be m of x, and it's the exponential of the integral of the coefficient of y, which here is just 2. Okay, so that is what we build up. Before we work with this, we'd like to do the integration step here. And notice there are big brackets around here. We do the integral all by itself and take the product or the result of that integral and put it as the exponent to base e. So in this case here, it's just 2x. Now, I'm going to give you this hint that there's no plus c required. If you were to include a plus c, let's just try that for a second. I'll include it in this example just to show you what happens, but we'll see why it doesn't play a role in the general case. So we have our integrating factor. Then what we do is multiply through the standard form both sides. Obviously, we can't just do things to one side, by that integrating factor. So I'm going to include this plus c, and we'll see what happens with it, along with the e to the 2x. So we'll have e to the 2x plus c. Let's actually put the plus c in red to make it obvious what's going on. So here's our standard form equation. We're going to multiply this by e to the 2x plus c times y prime plus e to the 2x plus c times 2y is going to equal e to the 2x plus c times 3e to the x. And if you take a quick look at that, you recognize that on the left-hand side, everything has an e to the c as a multiplier. So I could bring this out and call it e to the c, call it out of this. It comes out of both terms. And I could bring the e to the c out here. And so both sides have an e to the c. We would divide through by that because it's not 0. And what that effectively does is mean whatever plus constant we were to include here would be immediately canceled on the next step. So we just don't bother. Again, there's no harm in doing it. It just complicates your life. So we're going to avoid doing that as we go forward. Okay, so with no plus c, let's rewrite this a little more carefully in this more standard form we would see in a traditional example. So we have there e to the 2x times 3e to the x. This is what we would have as a second step after we've multiplied through by our integrating factor. What we should have and what we must have, if we've done this job correctly, and so we should check, is that the left-hand side is now the derivative of a product. And sure enough, we see here we've got a function and its derivative, and we have the other function e to the 2x and its derivative. E to the 2x times 2 is in fact the derivative e to the 2x. And what that lets us do is rewrite the left-hand side. We can write it as the derivative with respect to x of simply e to the 2x times y. And if you were to go through the calculations of the product rule and the chain rule, you would get exactly what we have here. That means we haven't changed the left-hand side, which means we shouldn't go changing the right-hand side, so I'll leave it as is. We will simplify the right in a second. I just want to emphasize that nothing has happened on the right-hand side yet. But what we've accomplished here is isolating a single derivative rather than this mix of y and its derivatives here. Now we have one derivative being taken of the entire left-hand side and that equaling some function on the right-hand side. Let's carry that over to the next page and see what happens. With the right-hand side, we could simplify it as e to the 2x plus x. We had e to the 2x times e to the x, and that's better known as e to the 3x. All right, now what we have is the derivative of something with respect to x is equal to this function here. Well, now what we can do is integrate both sides with respect to x. When we do that, what's going to happen on the left-hand side, the integral and the derivative are inverses of each other. They're going to cancel each other out. So when we slap an integral sign in front of here and integrate that with respect to x, I had a function, I differentiated, then I integrated, I get back to where I started. On the right-hand side, it won't be quite so simple. but it'll be a fairly straightforward integral to evaluate. But the key thing is when we integrate the left-hand side, we just end up with e to the x times y. The derivative and the integral are inverses. On the right-hand side, we do our usual integration skills now, and we recognize that e to the 3x over 3 would be the integral there. And we're going to put a plus c. I'll call it plus d because we had a c earlier in this question. And at the end of the day, we are ready to go because we now have y equals. So we note that there's no derivatives anymore. So we can simply solve for y. And once we do that here, we're going to have y equals, bring the e over, these 3's first cancel. We're going to have e to the 3x plus d all over e to the 2x, and that cancels out to an e, and we would usually write this as e to the negative 2x. So e to the x plus d times e to the negative 2x. And that would be our general solution. There's a factor in there that we didn't control. We can choose it to be whatever we like, and that should give us a family of solutions that all satisfy the original differential equation. Now, it sounds like a smart idea at this point with a new technique to verify that what we have actually is a solution to the differential equation that was given. So what we do to verify that is we simply sub in to the left-hand side and the right-hand side. To sub into the left-hand side, we're going to need y prime, though, which would be e to the x minus 2d e to the negative 2x. Remembering that d is a constant. It does not change with x, so we can do a simple derivative here, the exponential part. When we do that, we can evaluate our left-hand side, which is y prime plus 2y's. There's y prime. And 2y's, there's our y. And that equals e to the x plus 2e to the x is 3e to the x's minus 2d plus 2, hey, those cancel. So our left-hand side is equal to 3e to the x's. Conveniently enough, the right-hand side of our equation was exactly equal to 3e to the x's. These are equal. Check. And so we have that this solution that we proposed is a solution to the differential equation we were given.